Quantum computers promise to simulate complex molecules and crack current encryption standards. But to do that, engineers must isolate and manipulate individual atoms. Down at the subatomic level, hardware design has hit a physical wall. The issue is interference. Stacking more and more quantum bits, or qubits, onto a single processing chip eventually creates too much noise. The particles bump into each other, their delicate states collapse, and the entire system becomes impossible to control. In classical computing, there is an obvious solution to this. When a single computer isn't powerful enough, you plug a cable into it and network it with other computers to form a cluster. Physicists call this concept distributed quantum computing, or DQC. The goal is to build small, highly stable quantum modules and then link them together with physical cables to share the processing load. The timeline for building a useful quantum computer relies on this concept. The challenge isn't packing more atoms onto a single microscopic chip. The challenge is figuring out how to successfully network separate chips together. The standard method for networking quantum processing modules involves shooting individual photons, light particles carrying data, through fiber optic cables. But physical cables are lossy. As the photon travels down the glass tube, it scatters and fizzles out. Classical routers resend dropped packets, but quantum mechanics forbids copying information. If that single photon dies in transit, the calculation fails and the original data is destroyed. This specific bottleneck is the networking paradox. To scale up, we must connect quantum chips, but connecting them via optical cables risks destroying the math they are trying to process. A team of researchers at Oxford University recently found a way around this. In their lab, they set up an experiment with two separate quantum processing modules, placed roughly 2 meters apart. They named them Alice and Bob. To bypass the networking paradox, the team divided the labor. Inside Alice and Bob, they placed 2 different types of ions to handle 2 distinct jobs. The first ion, calcium, acts as a circuit qubit safe, holding delicate calculation data deep inside. The second ion, strontium, is the network qubit antenna, communicating with the other module through the optical cable. This dual-species architecture separates the math from the communication. The core calculation data sitting on the calcium ion is never exposed to the optical cable. To bridge the 2-meter gap without moving the data, the researchers used a technique called quantum gate teleportation. First, Alice and Bob's strontium network qubits shoot unhologrammed photons at a beam splitter to create a bridge of quantum entanglement between the 2 modules. Because these photons carry no calcium data, it doesn't matter if they get lost. The system simply fires photons until an entangled connection is successfully confirmed. As this diagram shows, once the system confirms a shared entanglement connection, the blue squiggly line, it performs a non-local operation. By following the local operations pathways, Alice and Bob successfully complete a joint mathematical operation without data ever physically traveling the gap. By using teleportation instead of direct physical transmission, the research team made optical cable loss irrelevant to the safety of the calculation. The lab results confirm the method works. During the experiment, the teleported CZ gate achieved a reliability rate of 86%. To prove Alice and Bob were functioning together as a single computer, the team ran Grover's search algorithm across the network. This specific algorithm is a major milestone because it requires the hardware to run several back-and-forth non-local logic gates, demanding a connection that remains stable over several steps. The distributed system executed the algorithm with a 71% success rate. This is the first time a distributed quantum algorithm using several non-local gates has been achieved. Multi-step distributed computing is no longer just a theory. The team showed it works in a macroscopic lab setting. This means engineers no longer have to rely on only one way to scale, packing more qubits onto a single, increasingly unstable chip. Instead, to increase a computer's power, engineers can manufacture more of these individual stable modules and link them through the teleportation protocol. This mirrors the history of classical computing. We moved away from giant, isolated mainframes and toward vast networks of modular data centers. Quantum computing is now positioned to follow a similar path. The Oxford experiment demonstrates a working model for how these decentralized networks can function outside of a single chip. By mastering the art of teleporting logic across empty space, scientists have established a pathway to expand quantum networks without being limited by the physical boundaries of a single processor.